frequency scale in IR spectroscopy is recorded in wave numbers, the inverse of wavelength. This is due to the fact that it gives convenient numbers. It is directly proportional to the frequency. Therefore, higher wave numbers correspond to higher energy vibration excitation. However, as it is the wavelength that is really being measured, the horizontal axis is recorded in decreasing wave numbers. Furthermore, at 2000 wave numbers, there is a change in the scale, so that the region to the right is more detailed. The vertical axis is calibrated as a percentage transmission. Thus, it is the amount of light reaching the detector that is measured, not the absorbance. This explains why the IR spectrum appears to be plotted upside down. The IR spectrum is split into 5 regions. 4000 to 2300, where vibrations occur due to single bonds to hydrogen, i.e. XH, where X can be carbon, oxygen, nitrogen or sulfur. 2300 to 1850 is the triple bond region. The double bond region at 1850 to 1500. 1500 to 1000 is the fingerprint region, and 1000 to 600, which is the unsaturated carbon-hydrogen bending. When analysing the IR spectrum, it's always start at high wave numbers and attempt to correlate the strongest absorption from the data tables. Also, take care to note the absence of peaks in characteristic regions, as this enables the ruling out of different functional groups. Do not try to assign every single peak observed in the spectrum, especially those in the fingerprint region. This region corresponds to the stretching vibrations of CH, OH, NH and SH. The high frequency corresponds to the small atomic weight of hydrogen, which dramatically lowers the reduced mass of the system. All these groups have similar reduced mass. Therefore, any difference in the vibration frequency must arise from the strength of the bond. The hydroxyl group requires the highest energy for vibrational excitation, due to its bond being the most polarized and thus having the highest force constant. The CH stretch, which is about 3100 to 2700. The stretch and absorptions of CH bonds are characteristically weak, because it's hardly polarized and so results in a very small change in the dipole moment of the bond. The CH stretch of an sp3 hybridized carbon occurs around 2900 to 3000 wave numbers, and thus can be distinguished between that of an unsaturated group, which occurs at higher wave numbers, typically around 3000 to 3100. However, it is most diagnostically useful. The most diagnostically useful CH stretches are those of an alkyne and an aldehyde. An aldehyde often has 2 bands in the range 2900 to 2700, whereas alkynes have a high CH stretch, typically around 3300. This stretch is generally not diagnostically useful, as nearly all organic compounds have CH bonds, and the stretching frequency hardly changes for different environments. The OH stretch, which is about 3600 to 2500. These vibrations are typically strong, due to the atoms having very different electronegativities, resulting in a large change in the dipole moment. Alcohols, phenols and carboxylic acids all contain the hydroxyl functional group. However, the wave number of the absorption does not distinguish between these functional groups. If no hydrogen bonding is present, the monomeric hydroxyl group will give a sharp absorption of 3600. However, generally, very broad absorption peaks are observed anywhere between 3500 to 2900. This is a result of hydrogen bonding, which varies in length and strength. Hydrogen bonding weakens the OH bond, thus decreasing the frequency of absorption. Therefore, the more extensive and strong the hydrogen bonding is, the lower the wave number required for vibrational excitation. Furthermore, as hydrogen bonds vary in length, they weaken the OH bond by differing amounts. This explains why broad peaks are observed which dissipate around a mean value. Alcohols tend to give a rounded absorption of about 3300, whereas carboxylic acids give extremely broad V-shaped absorbances at lower wave numbers as a result of formation of strong hydrogen bonding dimers. For example, due to higher extent of hydrogen bonding in carboxylic acids, benzoic acid has multiple peaks in the range of about 3010 to 2500. In addition, IR spectra can distinguish between hydrogen bonding, which is intramolecular, within the molecule, or intermolecular, which is between molecules, if the sample is progressively diluted. Intermolecular hydrogen bonding is dependent on concentration. As the concentration increases, the extent of the hydrogen bond also increases. However, intramolecular hydrogen bonding is independent of concentration. Therefore, if the solution is diluted, the peak becomes sharper, less intense, and shifts to high wave numbers. Now for NH stretching, which is about 3500 to 3300. NH stretching usually occurs in a similar region to OH, about 3300, but is generally easy to distinguish between the two, as NH peaks are not so broad, which is a result of smaller extent of hydrogen bonding. Furthermore, OH stretching is always accompanied by a CO stretch around 1250, which is usually more intense. Primary amines and amides can be distinguished from a secondary amine and amide by looking at the number of peaks. In an IR spectrum, an NH group gives only a single peak around 3,300. However, the NH2 group gives two equally tense peaks as a result of the two identical NH bonds in the NH2 functional groups, which have exactly the same force constants, reduced masses, and chemical environment. One peak corresponds to the symmetric stretch, which occurs around 3,300. The other corresponds to the asymmetric stretch, which is a higher frequency, usually around 3,400. The SH stretch, which is 2,700 to 2,400. The absorption is weaker for OH, as sulfur is less electronegative. The absorption is weaker for SH, as sulfur is less electronegative than oxygen, producing a smaller change in the dipole moment. Furthermore, it occurs at higher wavelengths in the range 2,700 to 2,400 due to an increase in reduced mass and the smaller force constant of the SH bond. 1850 to 500 wave numbers is a double bond region. This region corresponds to the stretching vibrations of the functional group containing a double bond to carbon. Thus the absorbent species are carbon double bond oxygen, carbon double bond carbon, and carbon double bond nitrogen. The carbonyl group is diagnostically very useful, as it corresponds to the strongest absorptions in the entire spectrum, due to the extremely polarized carbon-oxygen bond. Furthermore, the wave number of the absorption band is very specific to the type of function group present. For carbonyls of the general formula RCOX, the greater the electronegativity of the substituent X, the higher the wave number required for vibrational excitation. This is a result of the inducting electron withdrawal effect of the electronegative substituent, which effectively removes the electrons from the pi orbital, causing the pi bond to shorten in length, and thus strengthen. This effect is in competition with the conjugation by a lone pair donation into the carbonyl. This conjugation of the electron donating group with the carbonyl transfers electrons from the substituent into the antibonding pi star orbital of the carbon-oxygen bond, causing it to lengthen and weaken. Thus, the stretching frequency decreases, and the bond shows partial single bond character. Acid chlorides, therefore, have the greatest stretching frequencies, because as well as chlorine being very electronegative, it is a very poor electron conjugation due to poor overlap of orbitals. Thus, they typically absorb about 1850. Anhydrides also give large stretching frequencies, as the oxygen between the two carbonyls is highly electronegative. Also, the electron conjugation is weak due to the lone pair being pulled in both directions. Therefore, two high-frequency peaks around 1790 and 1810 are observed due to the symmetric and asymmetric vibrations of the carbonyl groups. In esters, oxygen withdraws electrons strongly, strengthening the bond. However, there is also greater electron conjugation due to the desirable overlap of orbitals. The inductive effect only slightly dominates, given a peak around 1745. Amides absorb at 1650, because nitrogen is less electronegative than oxygen. Thus, it has a smaller inductive withdrawal effect. Consequently, nitrogen is a stronger electron donor, as it holds its lone pair less tightly. So conjugation strongly dominates. This band corresponds to the carbonyl group that is referred to as amide 1. Amides also have a second absorption band in this region due to a higher, stronger NH bending vibration called amide 2. Amide 2 is usually less intense and occurs at lower wave numbers. Six-membered rings and larger rings have very little ring strain, and thus have little effect on the frequency of absorptions. However, decreasing the size of the ring causes the ring to become more strained, and angles become more removed from the ideal 120 degrees for an sp2 hybridized carbon. Some extra p character goes into the bonds of the ring, and the same amount of s character goes into the sigma bonds of the carbonyl, strengthening it. Therefore, as rings decrease in size, the ring strain increases along with the stretching frequency of the carbonyl group. The C double bond C and C double bond nitrogen are also present in this region, and the C double bond C of alkenes absorb in the range of 1680 to 1500. However, this peak is of low intensity due to the very small change in dipole moment of the bond. Aromatic rings show 2 or 3 stretching frequencies around 1600 to 1500. The carbon double bond nitrogen group typically absorbs in the range 1690 to 1650. The triple bond region is around 2300 to 1850. The absorptions in this region are due to triple and cumulated double bond systems. The C triple bond C stretching frequency of alkynes occurs in the region of 2200 to 2100 wave numbers. Most of the absorptions in this region are very weak, and as alkynes become more symmetrical, their intensity decreases, giving a change in the dipole moment close to zero. Nitriles absorb around 2260 to 2100 wave numbers. In addition, carbon dioxide absorbs strongly in the region around 2300, and bands corresponding to carbon dioxide are especially common in liquid films, when a reference is rarely used. The fingerprint region is around 1500 to 1000 wave numbers. This part of the spectrum comprises mostly of absorptions due to the vibration of the whole molecular skeleton. Thus, it is difficult to assign peaks to individual functional groups. However, there are some independent vibrational modes. Nitro and sulfonyl groups usually give rise to two strong absorptions between 1530 and 1350 wave numbers. The Cu groups of ethers, alcohols, acids and esters absorb in the range 1300 to 1050.